Hi guys! I couldn't find a good YouTube video to introduce KSP, so I'm just going to do a quick screencast of my PowerPoint and talk you through some of the concepts, and then you can do some practice problems on your own. So in this video, I'm going to go through these 5 discussion questions with you. We're going to talk about what is a solubility equilibrium, how do we write the equation, how do we write the equilibrium constant expression, and what does it tell you about the solubility of the salt? Then we're going to do 2 types of calculations. We're going to calculate solubility when you're given KSP, and you're going to do the reverse, calculate KSP given the solubility. So let's start with that first one. What does solubility equilibrium look like on the particle level? In this diagram, I've got 2 screenshots from the PhET, salts and solubility. So if we have a look at this PhET, if you imagine I dissolve a bunch of table salt, sodium chloride, you know lots of it will dissolve. The particles split up into ions and they're solvated by the water like this. However, if I continue to add salt, teaspoon after teaspoon after teaspoon, eventually we'll reach a point where the solution is saturated. If you have a situation like this where there is solid sitting at the bottom in equilibrium with dissolved ions, you've created a solubility equilibrium. This counts as an equilibrium because if you look carefully, particles are constantly popping off of the lattice and dissolving into solution at the same rate as ions from solution are precipitating onto the crystal lattice. More often, in solubility equilibrium problems, we're dealing with salts like this one, silver bromide, where it takes much less salt to get some on the bottom. This means the solubility is much lower. It's only a slightly soluble salt, and it's much easier to reach that equilibrium point where you have solid on the bottom in equilibrium with the ions in solution. So if we look at these 2 pictures, the one on the left is not the solubility equilibrium, that's just a solution, everything's dissolved. The picture on the right is a solubility equilibrium because we have ions in equilibrium with ions in a solid. Alright, question number 2. How do we write an equation for this? This is very simple. When you're doing solubility equilibria, the standard way to write it is to start with the solid on the left. So for the example I just showed you in the PhET, silver bromide is on the bottom, AgBr, solid, and it is in equilibrium with the dissolved ions. So all you do is split the solid up into its 2 ions like this. This gets a little bit more tricky when you have a salt like strontium phosphate, where there's a little stoichiometry to do. So strontium is in group 2, it has a 2+ charge. Phosphate has a -3 charge. So when you crisscross those, you get a mole ratio of 3:2. When that happens, you just have to be careful when you write your equation that you don't forget to use those coefficients in front of the dissolved ions. But that's all it is. That's how you write an equilibrium equation. Solids on the left, in equilibrium, dissolved ions on the right. Okay, 3rd question. Almost always in equilibrium problems, they're going to either ask you for the equilibrium constant expression, or you'll simply need to do it in order to do some math. It's very simple. It's exactly the same way that you would write Kc that we did at the beginning of the topic. So once you have your equation, you simply write K equals concentration of the products divided by concentration of the reactants. However, for KSP, the reactants are always solid, which means they'll never be included in the K expression, and you end up with a product of the things that are dissolved. And that's where this gets its name, K solubility product, because it's always going to be the ions multiplied by each other. Again, just be careful if you have stoichiometry, don't forget it. So for this second harder example, KSP is the strontium ions to the 3rd power, phosphate ions squared. Now, what does this number actually mean? If I go back to the PhET for a second, clearly table salt has a much higher solubility than silver bromide. And that will be reflected in the value of KSP. If we go to this third tab, Design a Salt, I've made a salt here with a KSP, if you look here tiny in the corner, of 1 times 10 to the minus 40. So it's extremely insoluble. And you can see what's happened as I've been speaking. It's almost all in the solid form. Very few ions remain dissolved in solution. That's what it means to have a really low KSP. If I increase the KSP rapidly by pressing on this arrow, watch what happens to the solution. Suddenly the solubility has skyrocketed and all the solid has been able to dissolve. That's what the magnitude of KSP tells you. All right. Now we finally get to the calculations. Our first calculation is, given a value for KSP, how do we find molar solubility? All right. We solved these exactly the same way we did KC problems the week before half term. Start by writing your equation. So in this case, the salt that we've been given is silver carbonate. So I wrote silver carbonate solid on the left and split it up into 2 silver ions and a carbonate ion on the right. From that, we can write an expression for KSP, which will simply be the silver ion squared times the carbonate ion concentration. And then you get to a little bit of a dead end here. We have the KSP, which is great, but we don't have either of the values for concentration. And we've been asked for the molar solubility of the whole salt itself. So we need an ice table. All right. So just like we did with KC, set up your ice table. I've got the equation at the top. If we're imagining taking the solid and dissolving it in water, the initial conditions are that there are no dissolved ions. It's all in the solid to start. Remember, just like with the K expression, solids are not included, so we can leave this column blank. When they dissolve, because of this coefficient 2, you'll always have twice the concentration of silver ions as you do carbonate ions. So I'm going to put a plus X for carbonate and a plus 2X for silver, which leaves you with equilibrium concentrations in terms of X. Now this part is slightly tricky. Molar solubility refers to the per mole of this whole formula unit of salt. Because there is 1 mole of carbonate in this salt, the mole ratio from silver carbonate to carbonate is 1 to 1. That means this value X, the concentration of carbonate, is the molar concentration of the whole salt, because they are a 1 to 1 ratio. So if we sub those values in and solve for X, we will have our answer, the molar solubility of this whole salt. So here we go. I've already got my KSP expression. I simply put 2X in for silver, X in for carbonate. Factor this out to 4X cubed, solve for X, and we get 1.1 times 10 to the minus 4 molar for the molar solubility of silver carbonate. Right? And you'll have a few examples of that to do on your worksheet in a moment. Okay, our second question, part B. In a saturated solution of silver carbonate, what is the concentration of each ion? See, we're not quite finished. We worked out the molar solubility of this whole thing. The question is now asking us, what is the actual concentration of silver versus the concentration of carbonate? This is quite a quick one. We already know the value of X, so we simply need to go back and use our stoichiometry. Carbonate, like we already said, is a 1 to 1 ratio with the salt. So carbonate's just going to be the same as X, 1.1 times 10 to the minus 4. Silver, on the other hand, is double. For every 1 mole of this salt, you have 2 moles of silver. So we need to double our value and get 2.2 times 10 to the minus 4 molar. Alrighty, almost there. Last one, number 5. If you're given the solubilities, you should be able to find KSP. So we're just doing the exact reverse of number 4. and we're solving for KSP. So let's have a read of this problem. They've given us some lead chloride. At equilibrium, the concentration of lead-2 ions is 0.0159 molar. What is the solubility product constant? And when you see that, SP, that's KSP they're asking us for lead-2 chloride. All right, as always, first thing, write your equation. Solid on the left. Don't forget your stoichiometry. There are 2 moles of chloride in the ions on the right. Next, write your KSP expression. So this one's going to be lead-2 plus times the concentration of chloride squared. Now we've been given one of these values. We've been given the lead-2 plus. We have not been given the chloride, but you guessed it, we can work it out with stoichiometry. So there's the one we've been given, the lead. Chloride is simply a 2-to-1 ratio with the lead, so we only need to double it to get 0.0318 molar for chloride. And finally, last step, plug and chug into KSP, giving you 1.61 times 10 to the minus 5. No units for KSP. You don't have to worry about molar cubed or anything like that. This number, its only significance for us at this point is whether it's very large or very small, to tell you whether it lies to the left or the right. So this one being very small just tells us it's mostly solid, very little has dissolved. Okay, so that's it. What we've done here in this video, first thing, talked about what solubility equilibrium looked like. It's simply a saturated solution, so you have solid on the bottom in equilibrium with dissolved ions. So for every ion that dissolves, another one precipitates back into solid, and that way the rates are equal and you've reached equilibrium. Second thing we talked about was writing equations for these. You always put the solid on the left and the separated ions on the right. Third question we went through was writing the KSP expressions. It's exactly like KC, and in terms of what this means, a larger value means you have a higher molar solubility. Finally, we did our 2 calculations. The first one, you were calculating the solubility when given KSP. In this kind of question, you always have to use an ICE table to find out the equilibrium values. Be careful, the molar solubility is the whole salt, whereas when you're asked for an ion, you might need to multiply by 2 or multiply by 3, depending on the stoichiometry in the formula of the salt, so don't forget about that. And finally, the last one we did was finding KSP. If you're given ion concentrations or solubility, just use the mole ratios and plug and chug. All right, that's it. If you have any questions, let me know.